Let f be defined in the following manner. So f is from R3 under R3 such that for every x, y, z, it does associate 0, 0, z. Okay? Our aim here is to prove that f is a linear mapping. So to prove that, we want to take any two vectors in R3, combine them, and check if they are in R3 as a linear combination. So what we do is we take two scalars in R, combine the vectors in R3, and see their image, and see if that's a linear combination of the two. So let alpha beta in R, okay, and also let x be x1, y1, z1. Let's call this one x1. Let x2 be x2, y2, z2. So we want to combine these two, alpha x1 plus beta x2. So we have alpha x1 plus beta x2, alpha y1 plus beta y2, alpha z1 plus beta z2. We want to prove that f of alpha x1 plus beta x2 is equal to f of x1 plus beta f of x2. Okay? So that's what we need to do. That's what we need to prove. Okay? Let's see what we get here. So f of alpha x1 plus beta x2, by definition, it's going to give us the third component of this vector. So it's going to be 0, 0. The third component is alpha z1 plus beta z2. This vector can be written as 0, 0, alpha z2 plus 0, 0, beta z2. And also we can take the alpha outside, because you know that if you have a vector, okay, let's say you have x1, y1. If you multiply alpha, okay, you can take it out, x1, y1. Okay? So it's like you have your vector is, let's call this one u. So u is x1, y1. So alpha u is alpha. So let's say this vector has, let me do it this way. Let's say that this is the x1 axis. This is the y axis. This is the y axis. So here, this is your alpha, your u, but alpha u, assuming that alpha is bigger than 1, it's going to be this one. Okay? So this stretching of the vector, it's going to affect the x and the y component. Okay? So now, here, we go back here, we can take the alpha outside, we get 0, 0, z2, sorry, 0, 0, z1. Okay? z1 plus z1 plus beta 0, 0, z2. This is alpha. What's this one here? It's f of x1 plus beta. What's this two? It's f of x2. Okay, so that means we have proven that the f of alpha x1 plus beta x2 is given by this expression. That means that our mapping is linear. In fact, we can see that given any vector, let's call this one u, that has this component. So this is x1, y1, z1 here. Okay, so its image is the projection on the z-axis. That's why we have 0, 0, 0, z1. So f of u is given. This is f of u. It's just this projection. It's just 0, 0, z1. Okay, So if we have alpha z1, that means we have stretched this vector by alpha, and that means it's linear. So we have kept that stretching by f. That means f is linear. So that it's like we have shown that f of alpha u is alpha f of u. Okay, but for us we need to do that for two vectors, and that's what we showed here for this simple and easy example. We will do more examples concerning these mappings like this. We'll add 2 or 3 more. I hope this helps.